Professor John O'Connell is one of the, for me, the leading experts in thermodynamics, if you want to know the theory and the teaching of it and the concepts and application. He's the person to go. It has been a pleasure for me to collaborate with Professor O'Connell. He's also the author of the book, Properties of Liquids or Liquid Solution, together with Professor Proutsnett. And also he has another book on property modeling. And I will not say anything more, John, but please go ahead.
Well, it's a great pleasure to join you. Are you seeing my full slides or just the screen?
You need to go to the presentation mode.
Okay. I don't know whether I can do that the way this is arranged.
No, you need to do that.
Well, it isn't responding is my problem.
It takes a little bit of time, actually. So,
okay.
Can you?
Okay, let me, I have two monitors, and part of the problem turns out that most of the time I can get it to do it, but today, as usual, when you need it, it doesn't work. Well, okay, let me try this then. Do you see that? No?
We see.
Nothing happened.
Can you make your screen bigger at the top?
Just a sec. Okay. No, see, this is not the presentation mode, and I can't seem to get it to go to presentation mode. I apologize.
You can select on the slideshow on the menu bar.
In the top.
In the top. Not.
Nearby the animation.
After yes. Animation says slideshow.
All right, I just clicked on it. Now, and what happens is it comes up on my other monitor, but I don't get that to show to you is the problem.
Can you stop your other monitor?
Let me turn it off and see what happens.
You can click on the slideshow in nearby the animation on the next.
It doesn't work. It doesn't see. It doesn't change it on here. Okay, let me.
I think if you have two monitors, maybe that is causing the problem. I would suggest, is it easy to remove one monitor?
Well, I have to I have to remove the right one. So let me now see what happens when I do it here. No.
Another way. Can you please share the screen?
You have in the background another one.
So say that again.
What I can see is that, no, in the background, maybe it's my one. Oh, yes.
Can you please share the screen again and select the maybe the PowerPoint one again?
Okay, I think I know what I can do. let's see, you aren't seeing anything. You see this,
We
right?
can see your slides, but we don't see it in the presentation mode.
Yeah, and what I need to do is to shut off one of my monitors. And all of a sudden, I don't know how to do that. Because shutting off the power doesn't do it. I have to shut it off on the computer. I'm really, oh, here we go.
Okay, I think now it has come.
Right, okay. So let me go back to this. Now you see it?
Yes.
Okay. All right. Unfortunately, let me say that getting started again, and I apologize for it. One of my sayings is that technology is great when it works. So yes, Rafiq, thank you for the nice introduction. Yes, it's true. You and I have been working together for more than 3 decades. And I'm going to show some of the things that we've done together. And hopefully the audience recognizes that there are 2 of those references that were on your list. We were jointly working together some years ago. So let me tell you about the objectives of my presentation. I want to provide some perspective on the origins and the use of properties. Rafiq has given you many models and where they fit into doing process simulation and so forth. I'd like to back up a little bit and show you, confirm what the basics are in thermodynamics and the connection to properties, so that when you're using them, you have the confidence that they are rigorous and as far as they can go, that is, their origins are, and then also where the approximations come in. Some of your questions were related to where is it that things are better or not, and comments about when models may or may not work. I want to distinguish between 2 kinds of properties for you that we've used to, again, has some perspective on what goes on. One we call some conceptuals and others measurables. And then we should talk about single phase and multi-phase properties. I've done some work on the issue of when can you use ideal concepts for models, or you don't need models, as opposed to non-ideal where models are needed. And I think then we'll do some example applications, in particular azeotropes, which check consistency and also solubilities. We'll mention something about sensitivity of results to modeling that you have to be aware of to try to understand whether your model is going to do what you'd like it to do. Finally, some connections of experiment and theory to modeling, and also optimizing property efforts and a summary. Let's see, what I'd like to do, oh, there we go. Get rid of that. Okay. So let's go to thermodynamics. The laws of thermodynamics are always true. They're not like traffic laws. You don't, as some people say, you don't mess with nature. Nature does things reliably. The problem with thermodynamics is that the relations that you see have no numbers in them. They exist as integrals or derivatives or whatever, but there aren't any numbers in them. So the first law, for example, is mass and energy conservation. And the way you can say that is you cannot get mass and energy from nothing, and you also cannot throw them away. And many years ago, it was more important. The first phrase was more important. Nowadays, the second phrase is really what we have, because pollutants and heat, as they might say, stay with us. And we have to figure out how to minimize the problems that come from the fact that you can't throw them away. The second law of thermodynamics is about nature's directionality. It always costs you energy and money to go against natural behavior. So when do we do this? Well, we want to take something that's dilute and concentrate it. Nature doesn't normally do that. We want to go from low pressure to high pressure. Nature doesn't normally do that. We want to go from low temperature to high temperature with heat. Well, that doesn't happen either. So this is doing any of these things is going to cost us. And it's due to irreversibility, then, which will increase the cost. So if you're doing heat transfer over a temperature difference, the greater the temperature difference, the higher the cost. If you do it faster in terms of changing the rate in which you're doing it, or if you're mixing, all of those will lead to increased costs. So if you want to save money and effort, in terms of your processing, you want to reduce the irreversibility, which means you want to reduce these kinds of differences and get toward reversible, in which delta T is 0, the rate of change is 0, mixing doesn't cost you anything, and so forth. Now, properties give quantitative descriptions of state variables. What I mean by that is, if I specify the state, for example, temperature, pressure, composition, and phase, then I know a value. I can consider a variable to be fixed by that. And when I change the state, the variable is likely to change. And measurables are observable and usually what we specify. For example, temperature, pressure, density, the number of moles of components, and so forth. Conceptuals are non-measurables. There isn't a meter for the enthalpy or for the entropy or the Gibbs energy or the fugacity coefficient or the activity coefficient. So you have to get those for models, and they're the ones that connect measurables to conceptuals to arrive at values. Here's a picture that comes from Ganny and O'Connell, this was not the first paper we actually published together, which was done in 1989, but a presentation of how to think about process models that process simulators, for example, do. They solve constraint equations and balance equations. Rafiq showed a number of those. We start with measurable variables: temperature, pressure, composition in mole fractions, number of moles, which species are you dealing with? And these go into constitutive equations, which we would call for property models. And the result will be the conceptual variables, which you can't measure directly, but they are the ones that actually appear in the constraint equations and the balance equations. So that's why property models are necessary. And while the balance equations and the thermodynamics are always true, property models are only sometimes true. So here's some property models. This is a picture of a process that was done by our good friend Ralph Dorn at Bayer, again, many years ago, in which there are various units: compressor, heat exchanger, reactor, distillation column, and so forth. And he lists the properties that would be used to evaluate and determine what the unit will do, how big it will have to be, and so forth. And among those, there are a number of conceptuals, like the enthalpy of vaporization, the saturation fugacity coefficient, the vapor phase fugacity coefficient, Gibbs energy of reaction, heat capacities, and K factors, which would be in a decanter, a liquid-liquid system, the ratio of activity coefficients of the species in the phase. So that there would be where you have to, when you're designing a process, you have to arrive at getting property values from the models. So what are the thermodynamic origins of what we call conceptuals? Where do they come from? Well, the open system first law defines the enthalpy of the streams. So this would be the energy associated with the stream coming in at a certain rate. And this would be the energy going out associated with various streams. and there can be more than one. And then this is plus the heat effects coming in and the power associated with work. And the sum of those terms is equal to 0. So this is where, if you want to, when you're solving the energy balance, this is where you need the models for the enthalpy difference as well as the rates of heat and work. The open system second law defines the entropy of the streams, and this is the same thing. The entropy coming in, the entropy going out, the heat, and in this case, to get to entropy, you divide each of the rate of heats by the temperature at which the heat crosses the boundary, plus the term we call the entropy generation. Now, the enthalpy, entropy, and so forth are state variables, whereas heat, work, and entropy generation are process variables. These will depend on what the process is doing. These will depend only on the state associated with what's going in and out. Entropy generation measures the process reversibilities. A reversible process has entropy generation equal to 0. And so again, when you have something more irreversible, as the irreversibilities go up, the value of the entropy generation goes up. Now, there's a consequence of that. It's always positive. And so if this goes up because of irreversibilities, then this is more positive, then these terms will have to become more negative, or, well, become negative and more negative. And the consequence of that, if it's heat or changing the temperatures, that'll have an effect on what goes on in the work, for example. So this is the connection between what is the cost of irreversibilities and work or heat or temperature or pressure that you have in a process. Now, the Gibbs energy and chemical potential and fugacity are conceptual state variables to deal with composition effects. So the Gibbs energy difference is the difference of H minus Ts, which is also related to the difference in the chemical potential between the state and a standard state. And this defines the fugacity. So to note that only differences can appear for conceptuals. So you have to have some kind of standard state in order to be able to get the value of the system you're interested in. Now, in phase equilibrium between two phases, prime and double prime, from the equalities of the chemical potentials of the components in this different phases are equal, or the fugacities are equal. And in reaction equilibrium, equilibrium is reached when the summation of mole fractions times the chemical potential of the species raised to the stoichiometric coefficient in the reaction is equal to 0. So when are models needed? Well, ideality usually means no models are needed. So for example, the equation of state for an ideal gas is the compressibility factor, PV over nRT, is 1. The fugacity is such that the fugacity is equal to the mole fraction times the pressure. If you're talking about an ideal solution, which we would talk about in a liquid, then the fugacity is the mole fraction times the vapor pressure, typically. The enthalpy difference, it would be simply a function of temperature, and you would integrate the heat capacity in order to be able to get an enthalpy difference. For reaction equilibrium, the equilibrium constant is equal to the product of the mole fraction times the pressure raised to the stoichiometric coefficient, and it's the product for overall the species. So those are simple, and of course life is not simple. So we have to worry about non-ideality, which means models are always needed. So where do the models come in? Well, in the compressibility factor, that would be the equation of state. In the fugacity, there's a fugacity coefficient. In the liquid phase, there's an activity coefficient. If you're talking about the enthalpies, there's what would be called the residual enthalpy, which is what you have put in as extra terms in the enthalpy difference. And there would be a model for that or a model for the heat capacity as a function of pressure. In reaction equilibrium, they wind up putting in the fugacity coefficient for each of the species. Evidence of non-ideality. So when do you know if the system's going to be non-ideal? Well, you can look at any system, and if you get two liquid phases, it's clearly non-ideal. However, most of the times, the only way you can know is whether your system, when you look at it, isn't described by the ideal equations. And that means you have to have some data about how the system is going to behave. So let's talk about single phase ideal gas compressibility factor, where it would be equal to unity. There was a paper that I wrote a couple of years ago in Chemical Engineering Progress, which is the publication of the American Institute of Chemical Engineers, related to whether one worries about ideality, non-ideality in vapor phases. So this would be the case in which we plot the compressibility factor as a function of pressure for different isotherms. And we do it for two different substances, propane, which is non-polar, and methanol, which is highly polar. And this is what the graph looks like if you're talking about methanol as a function of pressure for the highest temperature that we have. And this is what it appears on the saturation line, and this would be the low temperature. And you can see first off that the two substances are different from each other. And in fact, the propane, the compressibility factor is less than that of methanol at high temperatures, whereas it's greater than that for low temperatures. These are reduced temperatures, by the way, divided by the critical. And this is now the region in which the ideal gas approximation gives you within 2%, because this is 0.98. And this would be where the ideal gas approximation would get you within 5%. So if you're in this region, you may want to choose ideal gas because it's adequate for your purposes. That's where you decide how much error can you tolerate. Now, if we go to the first order correction, which is the virial equation of state, and this is where you add together, add the unity, you add a term with the second virial coefficient and the pressure divided by RT, and B, the second virial coefficient, is less than 0 over almost all the conditions that we deal with in processing. Now we see the plot where the compressibility factor is a function of reduced pressure for the same substance, the same conditions. You can see this is where the ideal gas is. If you simply put in the second virial coefficient, you've extended the 2% range all the way down to 0.78 in the compressibility factor. So you've gone a much larger range. And if you're willing to do 5%, then you can go even further. So this simple correction can often deal with you in terms of deal with problems if you're dealing with a gas phase. So here's another case. We're now talking about what is the residual enthalpy, which is the enthalpy minus the ideal gas enthalpy. In this plot, we're plotting the residual. So the ideal gas would be such that this is 0 over all range, all the values of pressure and all values of reduced temperature. And you can see what the curve is like. And the second virial coefficient model is within a 0.1 of zero. The second virial coefficient will take you good accuracy up to 10.1 in this region, which is considerable. So for example, let's consider a typical natural gas compression. And it would go from ambient to a temperature of say 650 Kelvin and to a pressure of 50 bar. So where are we on the plot? Well, the answer is we're right there. And if we want to calculate the work, we can calculate it as the ideal gas term and the non-ideal gas term. And then we can see what happens? Well, on the chart, the ideal gas term is 9. And it's not on the chart, but if you calculate it, it would be 9. The residual term turns out to be 0.09, so it's about 1%. And in fact, the second variable coefficient model says its correction is only 0.04. So this would be a case, you see, where you say, I'm not going to worry about a 1% error in how much my compressor might have to do in order to do this compression. So by evaluating the case in which you're looking at, you can consider whether ideal would work for you. Now let's go to fugacities of pure vapors and gases. The general relation for fugacity would be mole fraction times pressure times fugacity coefficient. So let's plot, and the fugacity coefficient is not equal to 1 when molecules can see each other. In an ideal gas, molecules don't see each other. And the fugacity coefficient is less than 1 when they're attracted to each other and greater than 1 when they're repelled from each other. So what does the plot look like? Well, it's a straight line as a function of fugacity versus pressure for a pure ideal gas. And it varies this way in terms of when the fugacity coefficient is put in. I'll point out that at very low pressures, the real slope, which comes up like this, matches the ideal slope because of the rigorous Gibbs-Duhem equation, which comes from thermodynamics. And we'll talk about that a little later. The point to remember is that the slopes match when you're at low pressures. So this is gases. Now let's talk about mixtures. Well, okay, here would be the case in which the mixed ideal gas would be less because the mole fraction is less than 1. And the real gas would be, mixed gas would be down here. Again, it's first off reduced by the fugacity coefficient and second relative to the ideal gas. And it's reduced relative to the pure ideal gas because the mole fraction is less than 1. Again, what we can comment is that the fugacity has a strong pressure variation for gases and a weak mole composition variation. So if you're going to be at low pressures, it probably, you don't necessarily have to worry too much about a real gas relative to ideal gas. But if you're going to go up in pressure, it makes a considerable difference. Now let's go to liquid mixtures. There's two ways in which we can deal with this. One is mole fraction times if you get pure fugacity, which we'll talk about, and an activity coefficient. Or it could be mole fraction times the Henry's constant times an activity coefficient. And I use star because this is to be distinguished because these quantities are going to be different. So the activity coefficient is less than 1 or is not equal to 1 when the molecules see differences between the other kind of molecules in the system and their own kind. The activity coefficient with a star on it is not equal to 1 when molecules see their own kind appearing in the mixture. So this is when their molecules are looking at other components, and this is when the molecules are looking at their own kind. So what does the plot look like? Well, here's the Henry's law ideal solution. The ideal solution, Henry's constant, is equal to mole fraction times the Henry's constant. And at mole fraction of 1, it's equal to the Henry's constant. The Lewis-Randall ideal solution is where the straight line, and it's the mole fraction times F pure 1 and the fugacity of pure 1. Now the real solution is what we're after. And you can see that it goes from the Henry's law at dilute solution to the Lewis-Randall law at concentrated solution. And this means that you have a strong composition variation and a weak pressure variation. Gases in the sense of how they respond to changes in the state. Again, the real slope matches the Henry's constant ideal slope at dilute solutions, so that it deviates. And also you note that there must be some connection between the gamma with a star, which is this value, and the gamma like this, which is this value. And the answer is gamma star over gamma is F pure 1 over H1, which is not a composition. Now, Rafik actually showed that to you, and hopefully this reinforces the idea that you can choose whichever way you'd like to do it. You can worry about an activity coefficient, or you can worry about Henry's constant. And it really depends upon whether you're dealing with dilute solutions or concentrated solutions. So what are some of the expressions for fugacities? Well, you use a fugacity coefficient as we've shown, and the second virial coefficient term would look like this, where the second virial coefficient is between two different molecules, and there are correlations for this. For cubic or higher equation of state, the fugacity coefficient is complicated. And as I think Rafik implied, you don't always need to do it, and you get into trouble with you want to do complicated calculations. So one of the things you want to do is evaluate whether you really need to go to a higher order equation of state. Traditionally, we use activity coefficients for liquids, and the activity coefficient and the pure component fugacity. Now, fugacity normally would be calculated as the vapor pressure times the fugacity coefficient in the vapor of the saturated vapor. And for an ideal solution, gamma is 1. And also the fugacity coefficient of the saturated vapor is the same equation that you evaluate the fugacity coefficient in the vapor phase, but you evaluate it at the state of the vapor pressure and pure component. And you have to do that because you want consistency when you're doing your vapor liquid equilibrium. And you can only get consistency with this particular formulation for the saturation fugacity coefficient and the vapor fugacity coefficient. Now you can use, as Rafik was pointing out, you can use the equation of state in order to get a fugacity coefficient in the liquid. It takes more computation time, and reliability can be uncertain. My answer to the question of whether what are the downsides of using a combined equation of state activity coefficient model is, as usual, any extrapolation that you use a model is always can be risky. But if you've determined the parameters for your model at low pressure, those forms of equations of activity coefficients from equations of state will take you to a higher pressure with some reliability. It's better to use it combined with the activity coefficient model than use it with a KIJ, which then modifies the parameters, because you generally have in vapor liquid equilibrium, you have activity coefficient models ahead of where you have data and tabulations of binary constants for equations of state. Again, it's perhaps unnecessary at low to moderate pressures. Now, if you're doing VLE, equal fugacities means you set two variables and solve for the others. This is basically what Rafik has also shown, and they're much more complicated when you actually put in all of the variables that appear in the equations of state and so forth. And the article that we did in 2006 describes how to count all the variables in there, as well as gives prescriptions for how you go about solving them. At lower pressures, it turns out that the ratio of the fugacity coefficients is about 1. So in this case, you focus on how to get the activity coefficient, because that's going to be the determining factor in what will settle the phase equilibrium. Oops. So let's talk about vapor-liquid equilibria a little bit. Let's talk about close boiling binary systems. One of the things you'd like to do would be to look at the ones that are close boiling, in the sense that the vapor pressures are close to each other. Those are the troublesome systems. And so we make a comparison of some systems where the ideal solution is compared with the result from an NRTL model. This is ethanol with isopropanol. Now, normally you'd say that's an ideal mixture. Well, here's the difference of the K factor, which is the ratio of vapor mole fraction to liquid mole fraction. And this is at a slightly elevated pressure. And you can see that the ideal and the non-ideal are quite close, but the values turn out to be not very far from 1. And the K factor of 1 is when you have an azeotrope. And we know for azeotropes, you cannot do separation by simple distillation. So here's ethanol and benzene. And here's the difference. You see the ideal is down here. And by the way, the ideal K factor is a straight line from one end to the other. And this is the non-ideal, which you see is significantly curved and significantly different from 1. But there is a problem, and that is, this is the azeotrope, the value of 1. There's an azeotrope right there. So you can get really good separation. K factors larger than 1 give you relatively easy separation when you're in this composition range, but you run into an azeotrope. Okay, let's look at another case. Here's cyclohexane and benzene. Here's the unity, which would azeotrope. The ideal goes this way in a straight line. The non-ideal goes like this. Now, this says that cyclohexane and benzene actually form an azeotrope if you believe the non-ideal model. So is the model right? Is there really an azeotrope? And the answer is yes. You look in the literature and there it is. And you say, but wait a minute, these are non-polar substances. There shouldn't be a problem with these differences in them. Well, let's talk about criteria for azeotrope, because we'd like to know as much ahead of time as possible about whether we're going to get an azeotrope or not. So simple distillation cannot purify azeotropic components. So how do you detect? Well, I suggest looking at the relative volatility, and I'm sure Rafiq talked about the relative volatility as a quantity. It's defined as the ratio in a binary between two components, the ratio of vapor to liquid mole fraction of component 1 to component 2. Now, if we put in what these are from our fugacity relations, we wind up with 3 different ratios. One is a ratio of the activity coefficients, another is a ratio of the vapor pressures, and a third is a ratio associated with vapor phase non-ideality. Let's look at these as we go along, one term at another. If we look at the effects of vapor non-ideality, what we'd like to find out is, when does this deviate from unity? And it turns out that the second virial coefficient term will give you the first order variation of that. And if you're talking about up to 5 bar, it turns out that it's only a few percent in the relative volatility, which often can be ignored, particularly when we're asking ourselves the question, will a system form an azeotrope or not? And I can point out that if you do the analysis for the vapor pressure ratio, you get a similar small effect of vapor non-ideality in these systems. And also in liquid phase reaction equilibria, you don't get much non-ideality. So the relative volatility is basically a composition effect. Now, if we plot the ratio of activity coefficients, this is the alpha gamma term, versus the alpha PS, which is the ratio of vapor pressures, on the same plot. And this is a curve which is where alpha is equal to 1. So that's the hyperbola of this equation. And if you're on this curve, you have an azeotrope. Now, what happens is that many different systems are on these, and what you get is you get one from, these would be azeotropes that are caused by close vapor pressures, because you see this is at low value of the ratio of vapor pressures, and others that occur because you get a large difference in activity coefficients. The ones that I showed you were benzene, cyclohexane, benzene, ethanol are here because their vapor pressures are very close. So typically you can think this is all there is, but on the other hand, you can run into cases in which some of these are at high activity coefficient or low activity coefficient ratios where these are less than 1. So but if you are able to estimate the activity coefficients, then you can actually arrive at a description. So let's talk about estimating alpha 1, 2 accurately enough to know about an azeotrope. So here's our alpha. These two we don't worry about. This is the alpha gamma. And the range of alpha from mole fraction 0 to 1 is going to be this quantity when it's 0, and it includes the activity coefficient at infinite dilution times the ratio of the vapor pressures at the boiling temperature of component 2, all the way to the case in which it's now pure component 1. So it's this, and you have the activity coefficient at infinite dilution of component 2 and its vapor pressure at the boiling temperature of component 1. Okay, so an azeotrope if alpha is 1 between these two limits. So you need only the infinite dilution properties to determine whether you've got an azeotrope. And you can see on this plot, this is alpha 1, 2 as a function of composition in some binary systems. Now these are, and you can see that here's the azeotrope line. And these are actually drawn in from data, but you only need to know about the limits in order to decide whether it's going to be an azeotrope. So this one, for example, is always on the side greater than 1, so it's not an azeotrope. This one goes from one side to the other. This one is always on the other side, or negative with alpha less than 1. And we're not sure about this one. So in fact, you'd want to go either make some measurements or go to some reliable data in order to find out if you actually got an azeotrope. Determining an azeotrope experimentally can't be very hard, because you go into the laboratory, you put the mixture in, and you boil it away until you find out if you got an azeotrope or not. And these plots are similar for ternary and higher order systems, so you can find out ahead of time whether you've got an azeotrope or not. Now, changing subjects, thermodynamics provides consistency among properties. What you get are the property derivatives, which are always true mathematically, and they have some, there are famous ones which have some names. For example, the Gibbs-Duhem equation, which relates the partial molar properties to each other. This is the generalized Gibbs-Duhem equation, where F can be volume, enthalpy, Gibbs energy, whatever. And the partial molar property would be the partial molar volume, the partial molar enthalpy, chemical potential, log of the fugacity coefficient, log of it. So any of these can be put into this equation. And you say, where did this come from? What's going on here? And the answer is, if you have a system with a certain number of variables, certain number of components, the phase rule tells you that the number of variables that you, if you look at this equation, the number of variables that are in it is the total number of components plus 2. There's one of these for each of the components, and then there's temperature and pressure. Well, the phase rule says you can only have one, C plus 1. So there has to be a relationship amongst these variables that appears, and that relationship is the Gibbs-Duhem equation. Unfortunately, it's a differential equation, and so applying it can be a problem, but it's there and it has to be followed. You just can't independently determine partial molar properties from each other. You have to always satisfy the Gibbs-Duhem equation. And so what this says is if the expression for one component determines the others. Now, if you model excess properties and then take their derivatives to get the activity coefficients, the Gibbs-Duhem equation is automatically satisfied. And so that's a strong reason for choosing a model based on excess properties as opposed to choosing a model based on activity coefficient by themselves. Another equation, which is known as the Gibbs-Helmholtz relation for heat effects in the Gibbs energy. This is the generalized Gibbs-Helmholtz relation. It's a derivative, G over RT, taken derivative with respect to T, and this would be a constant pressure and mole fraction. This then is applied to, say, activity coefficients and leads to activity coefficient temperature dependence of the partial molar enthalpy. If you're talking about the fugacity in a liquid, this turns out to be related to the heat of solution. And I encourage you to look at the article by Matthias in INEC Research, where he explores all of the consequences of the Gibbs-Helmholtz relation, and in particular, the problems that people have run into converting data or matching data for solubilities and the heats of solution. Relation leads to the Clapeyron and Clausius relations for vapor pressure and enthalpy of vaporization. So here's the relationship that would come out from the Gibbs-Helmholtz function, and this would be the Clapeyron equation, which is the difference between the enthalpy in the vapor in a liquid, or the enthalpy of vaporization, divided by the difference in the compressibility factor in the vapor and the liquid. And if you assume that the vapor is an ideal gas and the compressibility factor of the liquid is 0, you get the Clausius-Clapeyron equation. So there's an assumption in there. And the question is this a good assumption? Well, let's look at the data. This is now a plot of the enthalpy of vaporization, and I'm going to put in both the Clapeyron equation and the Clausius-Clapeyron equation. And there's several components in here. We've got nitrogen, propane, octane, and methanol. And we've identified the normal boiling point as this pressure. This is a function of temperature. I can't actually see that, but it should be. Anyhow, here's the normal boiling temperature. And if you talk about the rigorous equation, this is how it varies up to the critical temperature. And here, and this would be the Clausius equation, the Clapeyron equation. This is the Clausius-Clapeyron equation. And this is what you would get if you chose the value right at the normal boiling point. And this is true for each of the components. And if you look at it, you can see that even if you get the value at the normal boiling point for the, and use the Clausius-Clapeyron equation, you're not going to get the right value because there's a separation between the value of the rigorous equation and the approximate equation, which occurs all the way along. Only at low temperature, and this is really low temperature, below the normal boiling point, is this, the Clausius-Clapeyron equation, going to be rigorous. So you have to be careful about going from one set of properties to the other. But the Clausius-Clapeyron, the Gibbs-Helmholtz equation tells us exactly how to do this. So now let's talk about solubility. If we're talking about a gas in a liquid, that is the critical temperature of the component we identify as 1, is critical temperature is less than the temperature of the system, but the temperature is less than the boiling temperature of component one. That's what we mean by a gas in a liquid. And the fugacity relationship would be like this, because normally the solubility of a gas is limited, so we use the Henry's law expression. If you're talking about a solid in a liquid, then you have a choice. You can either do Henry's constant. Now, this is where the temperature is less than the boiling temperature of component one and less than the melting temperature of component two. And so you can, the solid will be described, fugacity be described like this. The liquid, you can have your choice. You can either use a Henry's law or get the to use the solvent. And in one case, you have to have the value of the fugacity of pure liquid to pure solid. And the other, you have to have a Henry's constant. So these would be where the modeling will have to come in. If you're talking about a single solvent gas liquid equilibrium, one of the things you do is that you can take some, if you get data, you can get the Henry's constant from the ratio of fugacity in the vapor phase divided by the liquid mole fraction. And you do that at low mole fractions. If you're talking about a single solvent solid liquid equilibrium, you correlate either the ratio of this quantity to the Henry's constant or this quantity to this constant. This was the form in which I saw an equation in Rafiq's presentation related to the enthalpy, the melting temperature, and the enthalpy of melting. If you're talking about mixed solvents, however, and often we have to do this, my suggestion is that you use excess solubility, which is defined as what's the solubility of the component in a mixture minus the summation of the mole fraction times the solubility in each of the solvents. That's equivalent to choosing an excess Henry's constant, which is the Henry's constant in the mixture minus the sum over the individual solvents. And there are approximations which exist. For example, the ideal solution approximation is that these quantities are equal to zero. The first order non-ideality is such that the mixture, the excess is equal to the excess gives energy of the mixture, solvent mixture divided by RT. So let's see what these look like. Okay. If you use excess constants, Henry's constants or solubilities, here's some advantages. One is that smoothness indicates consistency among the data. The small excess values for organics may be estimated, but it's a sensitive test of your models. For example, here's a plot of the mole fraction of solubility as a function of the solvent mole fraction for naphthalene, which is a solute, and water, and with organics. So the acetone and ethanol are the two cases here. This is what you get for the ideal solution, and this is what you get for the solubility in the mixed solvent. Now, if you plot the excess, then it looks like this. And instead of going from a finite value to another finite value, it goes from 0 to 0. Now, if you look at this, you can see that the excess gives energy expression doesn't work very well, because this is the experiment and this is the first order approximation. But you also see something else, I hope, on this plot, and that is this point and this curve just aren't right. And of course, that's, oops. And that's, of course, because there probably was a typo in the paper in which they reported this solubility. And in fact, I've been working with NIST on some papers recently in which we're looking at how reliable are the numbers that you get out of the literature. And their evaluation of a large number of papers for data indicate that 30% of every article published probably has at least one error in it, if not a lot. So one of the things that this shows you is that if there's an error in the data of this kind, it appears very obviously. It's there, but it's not necessarily so obvious when you do the excess property. Now, there's a variety of shapes of the excess mole fraction. Here's a set of different components that you can see. Here's the data, and they're mostly positive, but not necessarily always. And in fact, the modeling of these can be challenging, particularly for aqueous systems. This is an aqueous system, everything is fine. This is an aqueous system where it's really a problem. So the first order correction that you see doesn't do badly in this case, but this has got, it's sort of in the right magnitude here, but it misses the different change in sign. So what are the lines on the graphs? Well, these came from work by Martin Ellegard and published in 2009. We worked with Jens Abelskov at DTU, and you can see that these are generally successful. So it's worthwhile thinking about, if you want to predict solubilities, these are solids, from the models that are developed by Ellegard. Let's talk about sensitivity for a moment. The number of stages in a distillation are badly in error when alpha is off by a few percent. Here's a plot from our good friend Ralph Boddarn again. Here's the error in the minimum number of stages in a particular calculation. This is a function of alpha, and if you've missed, here's the result that you would get if you got it right. And this is what you get with different values of alpha. For example, this is 1.2, and this would be 1.05. And this is how much of an error you can make in terms of what percentage you get. So the sensitivity of this to a value of alpha is very high, particularly when alpha is close to 1. Another is the product composition can depend on property input. Here's a plot. You're associated with toluene and chlorobenzene, and you're doing this in a distillation column with 40 stages, and you feed in equimolar, and it's at atmospheric pressure. And this would be the proper value that you'd get, 100 parts per million of toluene in the bottom phase, no, bottom stream. And if you we're now estimating this by corresponding states using the critical temperatures of the components, and you don't get the right value of the critical temperature in there, so you change it by 1%. Well, it changes the mole fraction in the bottoms by an order of magnitude. Again, this is when you're dealing with the dilute solution, you've got to get it right. And here's a perfect example. Interesting is it's virtually a straight line on a log plot of how much error will occur. So let's talk about a view that I have on a structure of modeling. You want to start, what you're interested in is getting product design or product formulation and behavior. My concept of this would be to start with the fundamentals and then examine how this would be analyzed by a combination of theory, experiment, and what I call microsimulation, which would be quantum and molecular computation. And then those lead to models. And you look at what would each contribute. Well, theory gives you approximate results for idealized systems, but it does collect the variables in ways in which you can parameterize them. And so the model formulation often comes from theory, There's theory, for example, in local composition models, as Rafik was pointing out. There's a theory associated with group contributions, and it collects those variables and descriptions and parameters in ways in which you can parameterize them and get numbers. Microsimulation augments this, and it's essentially exact molecular physics and chemistry, but it uses approximate microinteractions and electronics. So it isn't completely reliable, but on the other hand, it can give you a verification of whether what you're looking at is proper. Experiment is essential. It's our only direct measure of nature's behavior. The problem is it only leads to empirical correlations, not models in the sense. So what you need to do is to bring them all together. And that's what people have done with the models like Rafik was talking about. So what are the ways in which I encourage you to do model formulation? Well, for one thing, remember what you're trying to get. If there are data and parameters in the literature, check them. You might run into one of those 30% papers. So the numbers are not, and the parameters are not always reliably communicated. But you can usually analyze whether you're getting something that's reliable or not. If the model has been established, but there aren't any parameters, you should take enough data to get values, unless you believe in estimation methods like group contributions and so forth. If the model form is okay, but you're not sure how reliable it is it going to work in your case, you should explore what the results are at different limits that you're going to, and see if the consequences at these extremes make sense and are consistent with what behavior would have to be in your process. If the current models are inadequate, then you're going to have to take enough data to test your model ideas. If the model form is even unknown, then the interactions are undetermined. Then what you have to do is find the phenomena associated that's most important to the situation. You do molecular measurements like spectra and colorimetry, for example, and you can do microsimulations to reveal structural effects. And if the behavior that you have would really make a difference in what the consequences are, take the simplest data first. For example, get a boiling temperature. Look at whether the boiling temperatures are close to each other. What's the melting temperature? Are you going to be dealing with solid phases or not? Is there an azeotrope? You get liquid. Is there microstructure like micelles in your system? All of these would make a real difference in what your processing would be like. And you better know about this in advance. So what's the summary? Well, what we want are good enough values for practical process designs and product behaviors. We don't have to do things too fine. It has to be good enough that our process or our product are going to do what we want them to do. How complicated should models be? Well, the old axiom is it should be as simple as possible, but no simpler. So the accuracy and information needs can vary. Just put in just enough effort to meet your objectives, which also include how accurately do you want your model to be. How do you generalize? Well, you got to look for consistency, and you got to know the sensitivities to the results. And you should try to optimize the problem of accuracy and reliability versus convenience. Accuracy and high accuracy and reliability take a lot of effort. Convenience is, well, that's low effort. On the other hand, if you get too convenient, you're probably not going to get enough accuracy and reliability. That's why that's an optimization problem. Think about that relative to the two possibilities when you're evaluating your system. So how do you economize? Well, I encourage you to minimize, first off, measurement. Data are essential, but they take too much time and money and for all the needed property values. So you need to take just enough data to parameterize and validate your models. And if you're willing to go without any data, it's risky, but that's the decision that the engineer makes. You should minimize decisions and specializations of the models. So you develop concepts, relations models for the range of properties, conditions, and processes of the project. In other words, don't overdo it, but on the other hand, make sure that you've got everything covered in your project in terms of models and where they apply. And you should minimize computer resources in terms of calculations, times, and so forth, as well as programming that you have to do. So you consider how do you be most efficient in your work in order to minimize your time and effort. So thank you for your attention. I'm happy to hear your comments and answer your questions. I understand you should use the raised hand icon to get permission to unmute and ask.
Thank you very much. Okay, so the floor is open for questions. Maybe I can ask one question, John.
Sure.
To this study of the isotopes was very interesting. Is it possible to very quickly look at two compounds or a series where one compound is fixed and the other compound is changing to say whether the pairs, which pairs would be forming isotope or not?
Well, there are, again, what you could look at is when you change the identity of one of the compounds, what does the relative volatility do at a limit, which means what does the activity coefficient at infinite dilution do as a function of structure? And you can often make an estimate of that from the group contribution method. That would be the first thing I would try in order to see whether, as I go from, say, chain length for hydrocarbons, or change the group from a hydroxyl to a keto or something like that, what happens to the activity coefficient at infinite dilution, which would tell me what the relative volatility will do at that limit.
The problem is that I'm trying to look at some of the refrigerants, and also it turns out that those group contribution methods, including ours, don't work for small molecules.
Well, certainly that's true. One of the things, though, is that the difference between the group contributions for changing one element of the structure, one of the groups, for example, is probably more reliable than predicting the activity coefficient itself. So if you know, for example, what's happening in one pair of components, you want to look at what the group contribution would predict for the ones you know, even if it's not right. And then you estimate what would happen with the other. The difference between the estimates from the group methods and the data would be more reliable than just doing the activity coefficient in infinite dilution. You understand what I mean?
Yes, I will try, because it turns out that people are looking, they have been looking for some time now, that they would like to have the new refrigerants that form isotopes, because if they form isotope, then they will behave like a pure compound, since the vapor and liquid will be the same. I do see the advantage, but the isotope may also change with pressure, and then it will not be the same. So
yeah. Well, the one advantage of the infinite dilution activity coefficient is that you don't have the contributions from one compound with itself. you're only talking about contributions between the compound groups and the solvent groups. So you remove a lot of the uncertainty that appears or errors even when that you might get from two groups that are the same on the same molecule appearing in your calculation, because at infinite dilution, those contributions don't appear.
Okay, are there any questions? You can write to Professor O'Connell or send us your question and we will
Sure.
forward it to.
I'll be glad to. Let's see. Did you put in the material, my email?
We will send out your email address. Then we didn't put out in the material.
Well, let me write it.
Maybe you can write it on the chat box. Then
Yeah,
we will-
that's what I'm doing.
Okay, while Professor O'Connell is putting his email address, we are also getting ready for the next and last presentation today. This will be a presentation of our software called ProCape that has a lot of features. It's not possible to show all of them, but a selection of them will be shown and the others will be discussed. So we have a joint presentation by Orakoch and Konkanok. Okay, the email address is shown on the screen. So,
Okay. So I'll stop.
okay, so thank you, John, very much.
Sure.
And
I hope it's been helpful.
to me, yes.
Good. All right. Bye-bye.
Okay,
It's still very early in the morning for me.
yes.
Sorry that I
Yeah,
was
thank you very much for getting us, giving this lecture all the way from California very early in the morning.
Well, it's the only downside of living in California.
The mountains behind you, are they real Californian mountains? Or-
That's the Lee River.
Okay. No fire.
A picture I took when I was with my older son on a 5-week trip to China.
Okay. Oh, it is in China.
Yeah. Yeah.
Okay.
The Chinese people and some tourists would recognize that immediately.
Okay.
Yeah. Bye-bye.
Okay. Bye-bye. Thank you very much. Okay. So Konkanok and Orakoch, you're ready to go?
Yes. Okay, we will start share the screen.